So we'll start in 2 minutes time. So we have discussed about the concept of velocity potential function and concept of stream functions. Let's discuss something about the physical significance of stream functions. No, 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 no. Today, how it is possible? 10:50 already will be there, right? No. So not on the physical significance of physical significance of stream function. Sign. So consider a flow domain like this. Here we have the y. Here we have the x. Now you try understanding here what we can have the streamlines psi 4, psi 3, psi 2. This is nothing but psi 1. Not visible. Just wait. Now it is visible. So physical significance of stream function where we will discuss. We have taken the four streamlines which are parallel with each other, just like a laminar flow which is there. Now here, what I'm just saying to you, and these streamlines are constant streamlines. These streamlines are constant. Like they will not change along the line. That stream function will not change. This will be the constant. This is constant, right? So here, what I'm saying, d psi total d psi when you write, what you can write according to from maths, total differentiation of d psi, what you can write, dou psi by dou x into dx plus dou psi by dou y into dy. So d psi we can write. See, what is a dou psi by dou x? What is the u value? What is the formula for u? Dou psi by dou y. And what is the formula for v? Dou psi by dou x with the minus sign. Getting my point. So here what we can write here, but there is no vertical component of velocity because we are taking psi as a constant. So this will be zero. So what we can write? What we can write? This will be zero because dou psi by dou x. When you just move along the x direction, let's say from here to here x1, and from here to here this is x2. Dou psi by dou x will be zero. Dou psi by dou x will be zero. D psi, and what is this? This is nothing but u. So this will be u into dy. what we can write when you just multiply with the width into width, so what you will be getting, d psi will be equal to u into width into dy, right? Dy is a distance from two streamline, distance between the two streamlines. So what you will be getting, you will be getting the some flow area, flow rate, like this. This is a width w, this I'm calling width w, and here we have dy, that is a distance between the two streamlines. And here what we can have, what we used to write, this charge a into velocity, right? And what is the area, what is the area, my different area will be, tell me guys, dy into width, that is the area through which it will flow when you just consider the three-dimension view of that. Now d psi will be q into 1 divided by what, width. So difference between the two streamline, difference of two streamline, like psi 2 minus psi 1, if I just take the mod, it will give me discharge per unit width. Make a note of it. Dou psi by dou x will be 0, not d psi. Remember that. Now, once it is done, let me know. This is also constant. This is also constant. Yes, yes. Discharge or volumetric flow rate, both are same. Q discharge, volumetric flow rate, all are same thing. U is this one velocity, this velocity U. No, that is for all. For a very general case, this we are discussing. For a 2D flow, it is valid. So this formula will be valid for 2D, like 2D flow. Equipotential flow, that is a different thing. Equipotential flow is about, they are talking about d phi, that is phi will be constant, right? That in that case phi will be constant, velocity potential function will be constant. Not d psi by dx or dou psi by dou x, or what you can write here, it's better to say dx is 0, dx is 0, right? Because when I move from here to here, from one point to another point 2, I'm moving along the constant x. Or if I'm just calculating the discharge from here to here, point number 3, or let's say 1 dash to 2 dash, so I'm moving in a y direction, so I'm taking this dx to be constant, right? See, both are 1 and 2 point, both are at the same distance from the inlet section, so dx will be 0, rather to say dou psi by dou x will be 0, right? So that is a not a good thing. So you can write dx will be 0 directly. Getting my point, all of you? That's why we are writing this d sign between the 2 points, not along the same streamline. We are writing across the streamline, right? Writing this across these streamlines. Getting my point, all of you? I think now the doubt will be clear. So some of you, I think you might have the doubts. Dx will be 0, not dou sine by dou x, because I thought we are applying on the same streamline, but we are not applying on the same streamline, because if you apply along the same streamline, d sine will be 0, right? For the same streamline, for the same streamline. Correct. Correct. That is for the same streamline, but we are writing for the across the streamline, two streamlines, psi 1, psi 2, and in between that there will be discharge per unit width. Now, once it is done, let me know. Is it done, all of you? No. See, along the same streamline, you have the sign constant, right? This is a constant. It will not vary. So better that you don't write this thing. Please do not write. D psi will be 0 directly. That is a this we are talking about equi-streamlines. Equi-streamlines. Getting my point? Is it done? Can I move to the next one? Please note down fast. Please join the class on time, guys. I cannot wait actually. This is a dy. Dy is a gap between the two streamlines. Dy. This is a gap between the two streamlines. Now, when you see this
sir,
one, hello.
Sir, can you go to the previous slide, sir?
Yes.
Sir, here we are doing a partial differentiation with x, no, sir. That means we are assuming y is a constant. Then, if you assuming
We are
y is a
assuming
constant, then
no. We are assuming x is a constant. From
no, sir.
let's say from
If
L
if
x for 1 and 2, both the points x is same, right? Dx will be
sir,
0.
so if we are doing d psi by do psi by do x, that means we are doing a partial differentiation, sir. That means we are assuming y is a
No, no.
constant. That means
Psi is actually a function of both x and y, right? So by the mathematics, we can write d psi equal to dou psi by dou x into dx, just like what we write some other function, right?
yes, sir.
Plus dou psi by dou y into dy. Initially, it was the function of both x and y, but we are writing. This is a very general equation, but we are converting this equation for across the two streamlines, keeping x constant, right? 1 and 2, for 1 and 2, x is constant. For 1 dash and 2 dash, again x will be constant. Maybe this will be x dash. Now, so this is a sine function they have given in the problem. They are asking what is the flow rate across the line joining A and B points. So flow across the A point minus B point. If I just take the difference, I will be getting the flow rate. Or simply I will call this to be discharge. Now please tell me answer, guys, very quickly. Sine A will be at a point 3 comma 0. What is the formula we have? Directly put the values. Sine A 2 into 3 square into 0 plus x plus 1. X is what? 3 plus 1 into 0, that is 0 Psi at B, when you calculate 0 comma 2, you will put the values 2, 0. Again, that will be 0 plus 0 plus 1 into 4, that is equal to 4. So directly answer will be C. Now make a note of it. Is it done? Now try to solve this another simple problem. Streamline of steady two-dimensional flow through the channel of height 0.2 meter. The total height this total height is 0.2 meter. When you just calculate 0.2 meter, point 0.1 plus 0.05, 0.5 minus 0.10. So they are asking where sin is a stream function in meter square per second. Why the unit is meter square per second? Because discharge unit is what? Meter cube per second. But we are adding psi, that is equal to per unit width. Width is what? Meter. So that's how we are getting meter square per second. That is another thing. And between the two streamlines, whenever we take two streamlines, I will be getting one discharge. One discharge. Between these two streamlines, another discharge. Another discharge. Another discharge. So Q1 will be equal to psi 1 minus, suppose this is a 1, 2, 3, 4, 5. Psi 1 minus psi 2. Like that you can do. Psi 4 minus psi 5. Psi 5 minus psi 6. Sorry. Only Q4 is there. And at the end of the day, total volumetric flow rate will be Q1 plus Q2 plus Q3 plus Q5. Or you can directly write Q2 to be equal to psi 1 minus psi what? 1, 2, 3, 4, 5. 5 directly. You will be getting B, because 1 minus minus 1, that is equal to 2. Or you can do in this way and you can add it. Now, what is the slope of equistream lines and equipotential lines? What is the slope of equistream lines and equipotential lines? See guys, yeah, both when you multiply, that will be minus 1. Okay, fine. So here, I think all of you have noted down. Done. Now here, just note down equipotential function lines. Equipotential function lines. Let's say we have phi that is equal to constant, and here if I just take phi is a function of both x and y. From maths, d phi will be equal to dou phi by dou x into dx, dou phi by dou y into dy. Phi is constant, so this d phi will be 0, and by the formula we know that u is equal to what? We have defined dou phi by dou x, and we have defined dou phi by dou y. This is u dx plus v dy, that is equal to 0. This slope of this equipotential line, this slope, we are calculating the slope, this dy and dx. So dy by dx will be minus u by v, where u is a x component of velocity, v is y component of velocity. Similarly, we can define equistreamlines slope, the lines of a slope for equistreamlines. Equistreamlines where psi is constant. Psi is what? Constant. So what we can write, my different? D psi will be equal to dou psi by dou x into dx, dou psi by dou y into dy, and here if I want to calculate the slope of this equistreamlines, slope theta dy by dx, if I want to calculate, so this is 0 for a equistreamline because psi will be constant, so d psi will be 0. Then what we can write? That is minus v dx plus u dy, that is equal to 0. So dy by dx will be v by u. So let's say this is a slope m2, this is a slope m1, and what is the m1 into m2? When I do that, I'll be getting minus 1. Whenever the two lines, this line, this is having a slope m2, when this line, this is a slope having m1, when the two lines are, when we just take the product of these two lines, slope of these two lines, when they are, we are getting minus 1, that means what? Two lines are perpendicular to each other's. Slope of the m1 and m2 are perpendicular to each other, and that is how we are getting the flow net. Flow net is a graphical representation of equipotential line and equistream function lines. Equistream function lines, rather to say lines, we can write equistream function lines. It's a graphical representation of, you know, it shows of basically like a meshing structure where both phi and psi are valid, both are defined. That flow net is defined only for 2D incompressible irrotational flow. That is a physical significance of that flow net. So here when I draw the flow net, it is something like this. So when you draw the flow net, it will be like this kind of. So let's say this is my psi 1, psi 2, psi 3, phi 1, phi 2, phi 3. So I'm discussing a very little bit of that. Remaining thing will be discussed by aerodynamic faculty. So here when I take the slope of this one and the slope of this one, Both will be perpendicular. Always they will be perpendicular. Right? No, they will always be perpendicular. Low velocity, high velocity, medium velocity, any velocity. What is flow net? It is a graphical representation of as long as the flow is irrotational and incompressible. It is a graphical representation of equipotential and equistream function lines. What about M1 and M2? That will be always -1, right? Any condition we have imposed that if velocity will be very low, then only -1 we are getting. Nothing like that, right? High velocity means what? Turbulent flow. In turbulent flow also, if flow net will be there, even though high mixing will be there among the fluid layers, still this phi and psi will be perpendicular to each other. Getting my point? Try to see on Google flow net for turbulent flow and just check it out whether any mergings are happening or not. It will not happen. It is valid for 2D irrotational. Why it is valid for 2D? No, why not for 3D? And incompressible flow. Incompressible flow. Why not it is valid for 3D? Because psi is not defined for 3D. Psi is not defined for 3D. And why it is valid for irrotational? Because phi is there, and because of phi, irrotational. Right? Incompressible, then psi will be there. Right? Now for this to happen, for flow net to happen, del square phi will be 0, del square psi automatically will be 0. So the question they ask in aerospace, right, few years back, regarding one statement, indirectly they want to ask about flow net only. Now, once it is done, let me know we can start fluid dynamics. No, 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 yeah, we are generally calling, see, we are generally, actually, phi is a function of both x and y, right? In a particular flow field, you are defining the coordinate system, origin is there, and here x is there, here y is there, right? So at any particular point, whenever you are defining, just say you have solved an example, right? Let's say here, you can see phi, psi, it is a function of both x and y, right? Means you want to move the coordinates in x direction in the y directions, right? It is a 2D flow, so it is a function of both x and y. It is not only the function of y, it is not only the function of x. Getting my point? Why we are writing like that? Where it is gone. And why we are saying d phi 0? Because along this, what will happen? Means this phi is constant for all the lines. For all the line, phi is constant. So d phi anyway it will be 0, right? D phi anyway it will be 0. Getting my point or not? Yes or no, guys? Now tell me, do you know something about source and sink? Like, if I just want to draw the flow net for other types of flow, then what we can draw here? I just wait. Here we can write. Wait, actually, I'm moving in a reverse direction. Now try understanding what I'm saying. Now how the flow net will be for uniform flow. If I just say constant diameter pipe, let's say the flow is happening in a constant diameter pipe, how the flow net will be. Uniform flow. It will be parallel, right? This I can write psi 4, psi 3, psi 1, psi 5. And then how the phi will be? The phi will be perpendicular, right? Phi 1, phi 2, phi 3, phi 4. At any time they will be perpendicular. So it is an example of uniform flow. What the example we can have? Constant diameter pipe in which the flow is happening like this. Now whether it is a laminar or turbulent, the flow net will be like this only. Now when we have accelerating flow, how the flow net will look like? Can you tell me? The pattern will not be like a constant gap between the lines. Why, I will tell you. It will try to converge. It will try to converge as it is moving towards the this particular end. So when you see from here inlet section to here, the velocity has been increased. When the velocity has been increased, right, what is the discharge formula? Area into velocity. Velocity has been increased, right, and discharge is what? Discharge is basically the difference between the two streamlines, right? So this discharge will be constant. Now automatically velocity has been increased. For maintaining the constant discharge or to satisfy the mass conservation, area has to decrease in between the two streamlines. That's why area has been reduced. Here area is decreased. Here area is what? More as compared to that. If here area is what? A1. Here area is what? A2. Between the two streamlines, now A2 has been decreased and A1 has been increased. Means A1 is more as compared to A2. This is a streamlines. What about the pattern of phi? Like this: phi 1, phi 1, phi 2, phi 3. Right? At any point when you draw the tangent, they will be perpendicular. Similarly, what about decelerating flow? What about for decelerating flow? They will be like diverging from each other, right? Something like this. And this is my psi 1, psi 2, psi 3, psi 4. And we can draw like this. And the flow direction will be like this. Here the flow direction will be something like this. Note down. Once it is done, let me know. All the things you will discuss once again in aerodynamics subject, so you do not bother about that. Now what will be the source? How the pattern of streamlines? How the pattern of streamlines? Source means sprinkles. When I just take these sprinklers, so what will happen to these sprinklers? Water will be going and they will be striking and they will be coming out, right? And they will be start rotating by omega. So this will be basically throwing the water. So sprinkles are there. Sprinkles are the example of source, right? Now tell me, what about the pattern of streamlines for source? Where exactly? Circular motion is there. Circular means what? Circle will be there because when you draw the tangent, you will be getting the velocity vector, right? So definitely they are moving in a circular path because of a sprinkler. Example is what? Sprinkler. Now in this one, what you can write? Circle you can make. Different different circles you can make. Right? Like this. Or maybe you can just write not a circle one. Here, tell me guys, this circle will be for phi or sine? This circle will be phi or sine? No, I just thought of no. I just thought of swirling flow. No, not swirling flow. I am talking about source sprinklers. Now tell me, this circle is for phi. Now, how about the sign? What about the sign? It is radially outwards directions, right? Radially outward directions. Like this, can I make? Just check it out. Psi 1, psi 2, psi 3, psi 4. Because they will be directed radially outwards from the center of rotations. Getting my point? And this circle will be my phi 1, phi 2, phi 3. Phi 1, phi 2, phi 3. Correct. Yeah. Correct. That is correct. Now, nobody has confusion, right? Initially, I thought for swirling flow, right? Swirling flow, what will be the pattern of streamlines? If anywhere we have the huge amount of swirling, right? Then it will be a circle one. Getting my point? Yeah, correct. That will be a circular one. But here for the source one, it is directed upwards, directed in the radially outward direction. So we can write psi 1, psi 2 like this. We can show like this. What about sink? Any example we have for the sink? Wash basin, right? Whatever the water flow is there in the wash basin, they will be directed upwards. They will be directly like this, right? So what is happening with this one? They are directed what? Towards inwards or outwards? Inwards. Getting my point? So what we can write here? Again, the circle will be there for 5, and here, my dear friend, for this one we can have like this. You can have you can prove it with the help of equation also. So here you can write psi 2, psi 1, right? Because when you take source and sink at the same time, when you just take the source and sink at the same time, for example, what the pattern will develop? When you take the source and sink at the same time, my dear friend, what the pattern will discover? This is what the pattern doublet. You have seen that, right? When you take the source and sink at the same time, so when you draw like flow over the cylinder, right? Flow over the cylinder. When you just take the example, there will be combination. There will be pattern of streamlines. There will be pattern of streamlines. That will be combination of source and sink. Getting my point? That is a combination of source and sink, and both are placed inside the cylinder. This is a cylinder or sphere, whatever you can have. The pattern of a streamline, that is what has been developed. This is my phi 2, this is my phi 1. Yes. Now, once it is done, let me know. No, that will be discussed. That will be discussed by sir, aerodynamics, sir, because you have separate topic for this ideal potential flow theory. Now, tell me, ideal potential flow theory, what the assumptions we have made. Whenever the flow is assumed to be, let's say, potential flow on any surface, curved surface, then what will happen? Meanwhile, you can discuss and you can think of the answer. Let me start the fluid dynamics. Note down fluid dynamics. Note down the Bernoulli equations. Bernoulli equation is an approximate irrotational incompressible. Yeah. Bernoulli equation is an approximate relationship between the pressure, velocity, and elevation height, and it is valid in the region of steady incompressible flow where the net frictional effects are negligible. So here, no, I'm asking you. Suppose we have cylinder. We have cylinder, and the suppose cylinder has been placed in a wind tunnel testing machine, and U infinity is a flow which is happening flow over the cylinder. Now tell me in this case, my dear friend, you believe that there is a boundary layer formation and all? If I just take the flow domain like this, so you believe that there will be some boundary layer formations? There will be some velocity gradient, and there will be something called flow suppression will happen. That's how the region of wake has been formed. But my question is, when you study ideal potential flow, so suppose now my flow is what? Viscid flow, right? Means I am considering my flow to be like viscid flow, but if I just assume completely in viscid flow, then what will happen? Because of wake formation, pressure will be what? Very, very low. Pressure is very, very high. So there will be some pressure drag. There will be some pressure drag. But when I assume my flow to be in viscid flow, there will not be any pressure drag. That is for sure. Will be there any boundary layer formations? Will be there any boundary layer formations in case of inviscid flow? There will not be any boundary layer formations. And when there is a no boundary layer formation, no viscous drag, no pressure drag, even no questioning about the boundary layer separation. So if somebody will ask you whether boundary layer separation can happen for inviscid flow, ideal flow, no. Answer will be no, right? So that's a small discussion I would like to take. Now it is over. Now you can just make it as a note point, and you can note somewhere, because sometimes our mind doesn't go there, but actually it is very important. Bernoulli equation, when you write, so what is Bernoulli equations? So sum of the pressure energy, kinetic energy plus potential energy will remains constant always, just like a conservation of mechanical energy, right? Conservation of mechanical energy. Here P by rho g is a pressure head. If I multiply with the, if I just multiply with the term called, see, unit is meter, right? And if I just multiply, if I want to convert into pressure energy, what should I do? Here, this is what? Kinetic head. This is what we have potential head. This is what we have potential head. This is kinetic head we have and pressure head we have. Now, what will happen? What about the kinetic energy? Kinetic energy we used to write half of mv square. We can further write half of rho, or we can directly write, if I just want to write directly the kinetic energy, half of mass flow rate into v square. This is what we have, a rate of kinetic energy or kinetic energy we have, right? So, and what about the potential energy? Mgh or mgz. Similarly, what about the pressure energy? What about the pressure energy, my dear friend? What about the pressure energy? What we can write? What is actually meaning of pressure energy? When you think of the pressure energy, what you can write? See, pressure will be there, that is Newton per meter square. And if I multiply with the volume, then what we can write? Meter cube per second. So I'll be writing joule per second, that is watt kind of things, right? Energy in terms of per unit time. So here what we can write? What is the pressure energy? What is the pressure energy term representing? Anybody? No. You might be knowing the Bernoulli equation, but you might not be knowing about the what we call pressure energy term. Very good. Flow work. Now, what is the meaning of flow work and why it is required only in the fluid dynamics, not in the fluid statics? Yes. Now, when you understand here, so better you write this is nothing but pressure into volume, right? So directly if I write pressure into volume, so I'll be getting pressure into volume, right? P into V. That is like a flow work. That is like a flow work, right? This is nothing but flow energy. Minimum energy required for the fluid to flow across the control volume, or in the basically what? Basically to cross the control volume, this is the minimum amount of energy which is required. This energy will not be required for the what we call control mass system, right? For a control mass system, we do not require this thing. Why? Because see, for any what we say control mass, let's say this is the ball, we have only internal energy. But suppose this ball will be, we are treating like a control volume, and suppose some flow is happening over this one. So now we represent enthalpy, not by internal energy for our open system. Very good. So we write H is equal to U plus PV. So there, apart from this internal energy, we have flow work there also. So this extra flow work which is coming, that is what, you know, this pressure head or pressure energy. That is also required. Kinetic energy also required, and maybe fluid is there at some height. So pressure energy, I means potential energy, will also be having in the fluid element. So make a note of it. Very, very important. And of course, fluid dynamics, whatever the pipe flow and all we are studying, we are discussing about the open system only, right? Across which mass can flow, energy can transfer, right? We are not discussing anything about the closed system. Internal energy is valid, means if I talk about energy of a body or a fluid particles for a closed system, internal energy will be very good idea about that. But for open system, I cannot write U. I have to write enthalpy because U plus PV will be there. If PV will be zero, flow work will be zero, mass cannot flow. Again, that will become like a closed system. So if somebody will be asking you what is the meaning of pressure energy, you have to define like that. This is a very important. Now we have to see the assumptions in these equations, and that is a very important assumptions that we have to discuss. Done, all of you? Is it done for all? Now, try understanding what I'm just saying to you. Okay. This Bernoulli equation, what we are writing, that is valid for, that is also called as Euler momentum equation or Euler momentum equations along this streamline in a steady flow. But there is a slight difference between the Euler equation and Bernoulli equation. Anybody know that? We have discussed in Navier-Stokes equations. What we have discussed? We have discussed Navier-Stokes equation. Suppose we are writing X momentum equation, rho into Ax, that is equal to minus dou P by dou X plus mu body force term. When this viscous force will be zero, when the viscous force will be zero, then we have this equation to be called as Euler equation. Euler equation is valid for inviscid flow, but it is valid for both. It is valid for both incompressible as well as compressible. Compressible fluid and incompressible fluid. Right? It is compressible for both incompressible and compressible. Yes, it is only valid for inviscid and valid for both compressible as well as incompressible. So, your Navier-Stokes equation will become what? Minus dou P by dou X plus body force term. When can happen this situation? When this situation can happen? When Reynolds number is very, very high. What is a Reynolds number? Inertia force to the viscous force. When Reynolds number is very, very high, my dear friend, when Reynolds number is very, very high, your viscous forces will be very, very low. When the viscous forces will be very, very low, when the viscous forces will be very, very low, in that case, your Navier-Stokes equation will reduce to Euler equations. There is another case, put a note. When Reynolds number is very, very low, very, 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 very low, then what will happen? Inertia force will be not dominating, viscous force will be dominating. In that case, what we can write? This is nothing but inertia term. This inertia term will be gone. This inertia term will be gone, and you will be left with pressure term and this one plus body force. What this equation we call? Cripping flow. Yes or no, guys? All of you are getting my point or not? When inertia force will become very, very low, viscous forces will be very, very dominating. That will be a creeping flow, like just like a honey flow is there, right? Honey is a highly viscous fluid, right? When it is flowing, you will not feel anything, that it is just moving like a solid body only. Very, 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 very. Suppose you have honey. When you take out honey, what will happen? It is highly viscous fluid, right? So it will not at all flow that smoothly or that fluently. So that is nothing but creeping flow. Another example of creeping flow is, suppose you have object, right? Basically this particular object is traveling in the downward direction in an atmosphere. So you will be having, what will be there? You will be having buoyancy force, drag force. All the forces will be acting on a particle. This particle, right? This particle, whatever the flow will be there, that we can treat it like a creeping flow, right? Viscous forces are dominating in that case as compared to the inertia force, because particle is what? Of very, very small mass. Small mass means small inertia will be there, right? So that is like a creeping flow. Now, once it is done, let me know. Make a note of it. So Euler momentum equation, we have to write dp by rho. Not we have to write rho. We cannot take rho outside of this integration, because rho we are treating like a not constant one. We are generalizing this for compressible and incompressible both. Incompressible and compressible. So x momentum equation I have written, right? See, what is the doubt in that? No, you just go back to fluid statics. There we have discussed this particular x momentum equations. This is the viscous term, right? When the Reynolds number is very, very high, viscous term directly gone, right? I'm not saying that mu is 0. I'm saying this particular term will be gone. As this term will be very, very negligible as compared to inertia term as well as pressure term. This is the pressure term. This is the inertial term, or rather to say inertia term, right? How we have derived x momentum, what is the role? You please see this fluid statics lecture, right? We have discussed the short version of Navier-Stokes equations. Not with this complete term because that will take a whole one class for derivation of Navier-Stokes equations. Now, is it done for all? Can I move to the next one? So, yes. It is sum of the kinetic energy, potential energy, and flow energy of a fluid particle. ठीक है, sum of the kinetic energy, potential energy, and flow energy of a fluid particle is constant along a streamline during steady flow when compressibility and frictional effects are negligible. Now, just wait. Note down the assumptions of Bernoulli. Assumptions of Bernoulli equations. That is a very simple equations we have. What are the assumptions of Bernoulli equations we have? The flow must be inviscid. Flow must be inviscid. Now, why the flow must be inviscid? If it is a viscid flow, there will be some viscous effect will be there, and some of the mechanical energy cannot be conserved. Second one, flow must be steady. I'm talking about ideal Bernoulli equation. Ideal Bernoulli. What is the meaning of ideal Bernoulli equation? P by rho g, P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. I'm talking about specifically about this ideal Bernoulli equation. Remember ideal Bernoulli equation, but these assumptions are derived on the basis of this ideal Bernoulli equations, right? If you just follow these assumptions, you will derive this one. It doesn't mean that it is not valid for unsteady flow. It is not valid for compressible flow. You have the Bernoulli equation for compressible flow also, but that is a separate thing. You know, in Senjal textbook, when you go, you can find this the compressible flow, Bernoulli equations there also, right? Now here, correct. Flow must be along the same streamline. Flow must be along the same streamline. But this condition is there only for which one? There is the one important assumption is there. What is that important assumptions we have? Important assumption is that, tell me guys, even though in viscid flow we have, there is a no chance of rotationality, but still we are bothering about flow must be along the same streamline for rotational flow. Very good. For rotational flow, my friend, like a force vortex flow. For a force vortex flow, right? For a force vortex flow, when you are applying the two points, you have to apply Bernoulli equation between the two points along the same streamline, not somewhere here and there like this. One point is here, 1 point is 2 point is here. You cannot apply like this. Why you cannot apply? Because see, it is an invisible flow but rotational. Externally we have applied some kind of rotation. Fourth one, Bernoulli equation can be applied anywhere. Bernoulli equation can be applied anywhere in the flow field, can be applied in between 2 points, and that 2 points need not to be on the same streamline. For irrotational flow, for irrotational there is no chance of rotationality, right? And there will not be any some kind of streamline pattern to be destroyed and all, right? In case of irrotational, it is a inviscid, it is irrotational, there is no chance of rotationality, so we can apply Bernoulli equation between any 2 points in the flow field, right? Note on the fifth assumptions. What is the fifth assumptions we have? Anybody know that? Flow must be, or fluid must be incompressible. Fluid must be incompressible. Now, once it is done, let me know. Now, tell me on the basis of this theory, tell me, can we apply the Bernoulli equation? Can we apply the Bernoulli equation inside the what we call, suppose flow over the flat plate, boundary layer is there. Can we apply the Bernoulli equation from here to here? Let's say we have the streamline 1 and 2. Can we apply like this? Streamlines are there like this, suppose, for example. Point number 1, point number 2. See, inside the boundary layer we have viscid region plus rotational region is there. And you can apply the Bernoulli equation when you have inviscid plus rotational. You can apply, right, along the same streamline. Along the same streamline. Then tell me, why don't you think that whatever the airfoil theory lift is there, whatever the lift theory is there for the airfoil, right? Whenever the fluid is flowing like this, you used to say that upper region is what? We have the larger area, then what we can have? The lower portion is what? Lower portion, whatever is there, we have the higher pressure, and top phase, what we have? The lower pressure is there, right? We used to say like this for the lift theory and all. Tell me, guys, what is the theory we have? Please recall that. Whatever the lift theory is there, what we used to apply? What we used to apply for the lift theory? Upper region is a low pressure region, a very, very high velocity regions, right? Because air has to travel a longer distance. Here air has to travel from point number 1 to point number 2 a longer distance. Now to meet at the same point, it has to travel with some high velocity, and here it can travel from 1 to 2, 1 dash to 2 in a very short no shorter distance is there. So this velocity has to be low. So according to Bernoulli, what will happen? According to Bernoulli, what will happen? Tell me, guys. So here the lift theory will be saying that pressure is high, pressure is low, lift will be generated. But is that true? This particular theory, because my dear friend, whenever you take the aerofoil section, right, and whenever the fluid is flowing in that aerofoil section, there will be some boundary layer formations. This is the boundary layer region, viscous region, right? You cannot apply Bernoulli inside that, right? So definitely, whatever the theory was there, that is the incorrect theory. Incorrect theory for lift generation. So there must be a correct theory. What is that correct theory? Anybody know that? What is that Prandtl and Kutta theory? What is that theory? See, lift is whenever lift is there, lift has something to do with the curvature. You know, whenever we have anything curvature, right? So definitely curvature is there. So there will be some pressure gradient will be there, and because of the pressure gradient, lift force will be generated. And how that pressure gradient will be there? That equation I will derive dp by dr, that is rho v square upon r. This thing we will discuss. When you just apply the Bernoulli equation perpendicular to streamline, you will be getting two things. One is in the radial direction, other will be what? Along the z direction. So here you will be having pressure variation along the radial directions. The lift has to do something with the curvatures. That is a very, very important, right? But most of the time you will find this particular, yeah, whatever you guys are saying, that is also correct, but this theory is incorrect. Don't say in interview, right? How the aircraft is flying, don't say that particular theory, what the Bernoulli has said. Yeah, that is correct. Anybody know circulation lift theory? That is also there. Correct. Circulation lift theory, correct. You try to give the answer either by this, which I will discuss, right, and at the end of the course, how the aircraft is flying, or the circulation lift theory is there, that you give the answer, right? But whenever you ask any candidate of aerospace background, he used to say this particular theory: pressure is high at the bottom surface, and pressure is low, basically what, low at the top surface. So because of the pressure difference, this lift force will be generated. That is incorrect. The lift force actually has to be zero. You cannot generate any kind of lift because of that. No. Now, can I move to the next about this Bernoulli equation with the head loss? This is a real Bernoulli equation. When you just apply the Bernoulli equation between the 2 points in a flow field, point number 1 and point number 2, definitely some losses will be there, and this loss we call head loss due to friction. This thing we will discuss in laminar flow through pipes. Head loss due to friction. Now mechanical energy is not being conserved. Point number 1, total energy, this one. But point number 2, the total energy is not, means we made equal to E2, but when you just consider only this portion, E2 ideal, actually it has to be equal to E1, but it is not equal because some part has been taken by this HF. That is a frictional energy. Correction factor, kinetic energy correction factor and all, yes, that is also there. We used to write like this here, alpha 1, right, alpha 2, here we used to write, that is a kinetic energy correction factor and all. That we will discuss, no need to worry. But why we don't take that into account? Whenever you see any calculation, practical calculation also, you will see alpha is being neglected. kinetic energy correction factor. That kinetic energy correction factor will be taken as almost equal to 1.03 for a turbulent flow, right? In a real practical situation, most of the flows are turbulent flow, and the values of turbulent flow, basically kinetic energy correction factor is 1.03. Even for a laminar flow, when you consider alpha value is what, 2. So when you multiply 2 with the v1 square by 2g, the 2 multiplication will not change that much, right? In most of the flow situation, the pressure energy dominates as compared to the kinetic energy term. So multiplying with the 2 doesn't make sense until unless that flow is a very 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 laminar, very very low Reynolds number. But in case of, suppose, most of the cases we have the turbulent flow, right, in nature. Why we have the turbulent flow? Because most of the cases we encounter the situation with the airflow, right? And airflow which is having a very very low viscosity. What is the Reynolds number? Rho v L by, suppose, mu, right? Viscosity is very very low, so automatically Reynolds number suits up. Even though you have been flowing with a 5 meter per second or 10 meter per second, still viscosity is very very low for the air, such a way that Reynolds number suits up and it gives rise to the values of what? Turbulent flow, right? So what will happen in this case? We have the value 1.03. 1.03 doesn't make sense, right? Almost equal to 1. So we don't multiply with this alpha, kinetic energy correction factor, in actual conditions. But this HF is very very important, and it plays a very important significant role in pumping power, right? When we just pump it with the help of some pump, we have to supply extra energy, that is rho g q hf. That is what pumping, no, basically extra power we have to give. If we are not giving, we cannot flow that fluid. Now, once it is done, let me know. So whenever, don't try to give this particular explanation. I don't find this to be very accurate. Whether some, no, sometimes you argue that, sir, these are the, basically we have been telling that, we have been told from the childhood days, still we are doing the master or we have completed BTech, but our faculty used to say the lift has been generated by that only, because they may think that this boundary layer is very very small region. So we are tempted to think we are applying this P and velocity relation of Bernoulli away from the wall. But even though it is a very negligible boundary layer, how can you narrate that, right? Now, can I move to the next one? Now try to solve this particular question and let me know the answer with the help of Bernoulli equations. There is a tank, there is a liquid which is being flowing in a pipe of some S shape. They are asking what is the discharge velocity at the pipe exit here. What is the velocity? Let's say the point number 2. What is that? Yeah, that gradient effect is there, but whenever you try to argue with those candidates, those who give the explanation, they used to say that boundary layer regions are very very small as compared to the fluid domain, right? Whenever you do any analysis, you select the flow domain, right? Suppose you are taking CD nodal, in that analysis you are taking, then definitely you will take some domain. What is this? Some inlet velocity. This is what you have, what you call outlet pressure condition, no slip condition. And here when you take the axisymmetric model, so whenever we used to think of writing the no, whenever we do project using CFD simulations or ANSYS Fluent, we used to create the flow domain, right? This flow domain, my dear friend, which is being created in such a way that it is not too large, not too short, but it is sufficient to have the physical effect on a particular body or whatever the flow domain which are happening, right? In that case, what they will think that, so whatever the, even the boundary layer formations which are happening, that are very very small as compared to flow domain, right? So in that case they can argue, but I don't think so that is correct explanations according to my point of view. So you can apply the Bernoulli equation between 1 and 2. 2 points I have taken. So apply the Bernoulli equation between 1 and 2. P1 by rho g. What is the height? Let's say this is my reference. From the reference point, point number 1 is there at a height of what? H. And what is my Bernoulli equation at, this total energy at point 2? P2 by rho g plus V2 square by 2g plus this height will be capital S minus small h. Now P1 and P2 both are what? Atmosphere, right? Just at the pipe exit, pressure is what? P atm. Here, what is the pressure? At the free surface, P atm. So this 2 will be gone. What is the velocity at the free surface? Free surface is like a static fluid, right? And it is also there in a big tank. Suppose this is a tank and we are writing what is the velocity at point number 1. That is almost 0. This is 0. So what we can write? V2 under root of 2g small h. B will be correct. Here, why we are neglecting this one? Because we can write Q divided by area. Area of the tank, we can assume that very, very large, such that velocity will be almost negligible. Whether you consider here velocity, here velocity, here velocity. What about the velocity term? Tell me guys. No, tank area has not been given, right? In this particular problem, any tank area has been given. So whenever you have the reservoir we can consider the point, at any point velocity we can consider to be very, very small, right? Inside the tank, not inside the pipe. When you consider point number 1 here, for example, 1 dash, 1 dash will not be having zero velocity. It is having some kind of velocity. Getting my point? I'm just telling you inside the tank. Suppose here 1 double dash, that is 0. Getting my point, all of you? Yes or no, guys? All of your understanding? Now you can apply the Bernoulli equation between 1 double dash and 2. What you can write? P1 double dash by rho g plus V1 double square by 2g plus height. From the reference, the height is what? Same, only 0. P2 by rho z, what we can write? Plus V2 square by 2g plus h minus h. So here what we can write? P1 double dash. P1 double dash we can write hydrostatic pressure, that is rho g capital H plus P atm. P2 is what? P atm. This P atm will be cancelled out. H plus P atm by rho g plus this is 0, that is V2 square by 2g plus h minus capital H. So this P atm by rho g here also will be there. This will cancel out. This will cancel out. So once again you will be getting what? Under root of 2gh. That how now some of you might be again argue that, sir, you mentioned in the assumption Bernoulli equation applicable along the same streamline. Yes, They may have these streamlines like this. They may have these streamlines like this. 2 point, 1 point, even 1 dash are along the same streamlines. Same fluids are there. Fluid row here also fluid row, right? All the things are has been satisfied. Getting not yes or no, guys? All of you understanding? Assumptions are very important. If you are not able to understand assumptions, tricky question you may not be able to get. Once it is done, let me know. We can discuss few more constraints regarding uses of Bernoulli equations. Done. Here we have the practical some restrictions on the Bernoulli equations. Let's say ideal Bernoulli equation. I'm talking about ideal Bernoulli equation. The first one is steady flow, right? The flow must be steady. Second one, the incompressible flow, that is appropriate. If the flow Mach number is less than 0.3, we can assume that flow to be incompressible flow of incompressible fluid when the density changes are very less than 5%. In that case, we can assume the Mach number to be less than 0.3, and that flow will become what? Incompressible flow. Frictionless flow, inviscid flow, that we already talked about that, right? And flow must be along the same streamline. Different streamlines may have different Bernoulli constant, right? This one. But this is rare for irrotational flow. The Bernoulli equation is same everywhere, right? Irrotational means there cannot be any viscous effect, there cannot be any rotationality effect. So definitely we can apply Bernoulli anywhere. Done. So whenever sometime in the problem they mention assumptions that uh, Bernoulli equation applicable for incompressible flow. So they wanna say about incompressible flow of incompressible fluid. That is a complete statement. The hidden meaning behind that statement is incompressible flow of incompressible fluid. Right. Once it is done, let me know. Done, guys. Done. Yes. Is it over? Now, when you think of this model, let's say aircraft is model, is there not a prototype, actual one? I'm just we are assuming that to be a model one, which is being tested in a wind tunnel. So definitely, when the flow is there, there will be some boundary layer formation is there. So we cannot apply the Bernoulli equation, right? That is invalid. We cannot apply the Bernoulli equation in those regions. In those regions, we cannot apply the Bernoulli equations because of the viscid and rotationality regions, right? Bernoulli equation invalid. We cannot apply. Now, when the flow is happening, again there is a boundary layer formations. Again, we cannot apply the Bernoulli equations. They are also near to the turbine. But let's say we have the wind turbine which is being placed in this section. Again, we cannot apply the Bernoulli equation between 1 and 2. We can apply from 3 to 1, 2 to 4. We can apply. But in between this section 1 and 2, we cannot apply. Why we cannot apply? Bernoulli equation is not applicable. Ideal Bernoulli equation. Ideal Bernoulli equation not applicable. Why it is not applicable? Because some part of the mechanical energy has been taken by wind turbine, right? And this might defend this turbine maybe start rotating. When once it will start rotating, my defend, it may destroy or it may disturb the streamlined structure of the flow, right? Here, whatever the streamline is there, which is being converging like this after putting this wind turbine, they may start getting mixed. This streamline will be start getting mixed, right? The pattern of the streamline will be disturbed. The pattern of the streamline will be disturbed, right? So what we can write here in this region, streamline pattern may gets disturbed, right? If streamline pattern will get disturbed, if the streamline pattern gets disturbed, then mixing might be there. Mixing will happen. What will happen? Viscous or friction dissipation will happen. Friction dissipation. Friction dissipation may happen. Make a note of it. Once it is done, let me know. Right. The pattern of the streamline will get disturbed, guys. 1 and 2 point, we cannot apply the Bernoulli equation between the two streamline. See, it is a rotational region of the flow, but there cannot be guaranteed that inviscid region will remain inviscid in case of turbine will be start rotating, right? Because of intermixing in between the fluids, the friction might be generated, and that will take away some energy. Friction means what? Viscid, rotational. We cannot apply Bernoulli. It doesn't mean that we don't have any Bernoulli equation for a work producing device. Suppose we have two sections. Here we have the wind turbine, right? Here we have the wind turbine, which is producing the work, which is being generated to the which basically connected to the shaft of generator, and this generates the electricity, right? For example, this wind turbine we have. But here, what will happen when the flow is happening? We can apply the Bernoulli equation between 1 and 2. That is not the ideal Bernoulli equation, but modified Bernoulli equations we call, plus work of turbine, like this. That is a real Bernoulli equation, or rather to say modified Bernoulli equations. But ideal Bernoulli equation we cannot apply. Correct. Yeah, that is also, yeah, correct. That is also some of the energy can dissipate in increasing the angular velocity of turbine. Well, of course, how the turbine will start rotate. That is a basic principle, right? Whenever the fluid will start hitting the blades, the kinetic energy of the fluid will be converted to mechanical energy of rotor blades, right? Rotational energy of blades. That is a very basic principle behind this rotational phenomena of either wind turbine or any turbine, hydraulic turbine or steam turbines. Now, gas turbine, yes, correct. Now, is it done, all of you? Certainly the sphere case, we can apply Bernoulli equation in wake region. No, we cannot apply in a wake region also. In a wake region also, we cannot apply. I will tell you the meaning of that. That's wake regions, right? No need to worry. I will explain you that particular thing by question only. See. Now read this question and tell me the answer. The streamline pattern along this sphere, which is being there, or cylinder they have given. This cylinder, they have given only one dimensions. Other dimension, let's say this is like this cylinder, and the flow is happening like this. Flow is happening over the cylinder like this, right? Flow is happening over the cylinder, something like this. So now, when the flow will be start happening over the cylinder, oncoming flow is steady, irrotational, incompressible. So we can apply Bernoulli equation between any 2 points, 1 and 2. Even we can apply Bernoulli equation between 5 and 6. Can we apply the Bernoulli equation between 1 and 6? 1 and 6. They are not on the two. They are not along the same streamline, but on the two different streamlines. Still, we can apply. We can apply as long as the flow is irrotational, incompressible, is steady. But we cannot apply the Bernoulli equation between 3 and 4. This is a nothing but low wake region, right? The flow suppression has happened, and because of that, the wake region has been formed. This wake region is, my dear friend, this is a wake region. Actually, this is nothing but vortex. Now, what is the so special thing about the wake region? Wake region, there is a specialty about the wake region is that it is a low pressure region. It is a very, very low pressure region plus viscid region. Now, why viscid region? Because see, already we know because of the boundary layer formations, the flow has been getting de-separated. The flow has been separated like this, something like this. The flow has been separated. Flow separation line. Now, what is happening, right? What is the region behind the flow separation? The region behind the flow separation is the fluid near the solid surface comes to the rest conditions, right? And after certain point of time, they will be start reversing its directions. They will be start reversing its particular directions. When they will be start reversing in a particular directions, what will happen? Tell me guys. Huge amount of viscous force they will import, right? Because see, what will happen? Upcoming air which are flowing, this is the cylinder, upcoming air which are flowing, right? Because of the boundary layer formations, we know that already this is a viscous region, right? Already the boundary layer regions are highly viscous region. In that also, some boundary layer separations, flow separation has been occurred. So flow near the solid surface, near to the flow separation is very, very rest conditions, is like almost dead, right? In that also, the fluid layer which are coming, right, it is getting mixed with the this dead body. So that is also getting slowed down, right? That is the one bad effect of that. Even though some of the fluids from the back side of that is start flowing in the reverse directions, and they'll be start dragging that dead body all around the what? All around the surface of the cylinder. So again, that is what the viscid region. Now my question is, don't you think that is a very misconception about the flow separation? See here, we have the cylinder, and here we have the flow domain. Here, when you think of this region till here, it is like a velocity is increasing, pressure is decreasing. But again, this region is what? Velocity is decreasing, pressure is increasing. So adverse effect is there where dou P by dou x is greater than zero. Pressure is start decreasing, increasing, right? But tell me when the pressure will be start increasing in this direction, in this particular domain, that's why the flow is start reversing. So don't you think it should be a high pressure region, the wake region? Why it is of low pressure region? That is my question. You know that flow separation has been occurred because of adverse pressure gradient, An adverse pressure gradient means P is very, very high here, P is low here, let's say. That's why the reverse phenomena has been happening. So don't you think that pressure has to be very, very high? Pressure is very high here. Anybody know the answer, or should I answer it? Flow suppression I will not discuss separately. I am discussing through this question only. So be very, very attentive. Viscid region, we know that it is like a dragging one. So definitely it is not a inviscid, it is a viscid region. Correct. Energy loss will happen. See, here, my dear friend, whatever the pressure is increasing, that is total phenomena outside the boundary layer, the red color boundary layer. But my green color, which I am drawing right now, that is my separate flow suppression which has been taking place inside the inside this flow suppression. This wake will be start forming. When this wake will be start forming, my dear friend, and this is like a dead body, the flow has suddenly stopped. Fluid near to the solid surface has been slowed down. When it is being slowed down, what will happen? Total energy, whether it is a pressure energy, kinetic energy, potential energy, all will come down. So pressure energy also gone down. That's why we say it is a low pressure region. Even though you have the pressure very high here in the boundary layer regions or outside the boundary layer, right? But you don't have any high pressure region when the flow suppression has been occurred. This is a flow suppression line. And when the flow suppression lines has been happened, there's a no point of, there's a no validity of boundary layer theory at that section, right? That is invalid theory of boundary layer when we have the flow suppressions. You have the valid theory till this point, till this the flow suppression has not been occurred. The moment flow suppression has occurred, there's a no point of talking about boundary layer theory. It is invalid, right? Here you can see, I'll make here this green color. This is the flow suppressions, and this is what we have the boundary layer, the black color one. Now, once it is done, let me know. Done. So the last problem I will discuss, actually, remaining part I will discuss apart along with this pitot tube and what we call pitot static probe. This is the question. Let me know the answer. What is the answer for this question? See, guys, Bernoulli equation is valid under steady state conditions only along the any 2 points in inviscid potential flow. Potential flow means irrotational, incompressible flow. Irrotational, incompressible flow. See, all of you done the mistake. Anyone know the correct answer? See, between any 2 points in both inviscid flow and potential flow. See, inviscid flow, you can have inviscid flow plus irrotational flow. You can have inviscid flow plus rotational flow. I told you one example of what? Force vortex. So we cannot apply the Bernoulli equation between any 2 points in this one. Suppose here and here, point 2. Bernoulli equation total energy we cannot equate. E is what? P by rho g plus V square by 2g plus Z. Total energy that cannot be constant between any 2 points. But if I take here 1 and 2, I can write E1 equal to E2. They are mentioning the two conditions. One is inviscid flow. Second, they are mentioning potential flow. When I take any potential flow, potential flow is what? Irrotational plus incompressible. And all the irrotational flows are inviscid flow. So we can apply Bernoulli equation between any 2 points in that potential flow. That is a valid statement. But between any 2 points for an inviscid flow, we cannot apply Bernoulli, right? So only along this streamline, if you are having this streamline 1 and 3, then only you can apply E1 equal to E3, right? In the inviscid flow, and between any 2 points in a potential flow, A will be correct. So sorry, make a note of it. What is the D statement? Only along the streamline in both. See, potential flow anywhere we can apply, right? So again wrong. C, between any 2 points in inviscid flow, again wrong. This is wrong statement. And only along this streamline, that is also we can apply anywhere. So example is force vortex. So they want to test through this question whether you know about force vortex or not. So you can see that in GATE exam they are testing everything. They are not at all leaving any single topic also, minute topic of important segments. Once it is done, you can leave for the day and try to solve the remaining problem which is being there in the slides. Thank you all. No doubt. Done for all. Okay.